All right, well, welcome to week 4. We're going to keep plodding along here. Our goal today is to continue our discussion about the graphs of sine and cosine. We started getting to that a little bit before the first exam, but we're going to kind of finalize that, talk about all the different transformations, what they do. We'll actually use sine and cosine to model something in the world that is something we experience all the time. And then we'll turn our attention to the graphs of the other 4. They're not nearly as useful in terms of the applied world, but still interesting. And so we definitely want to look at their graphs. So that's what today is going to be. It's really going to be a lot of graphs, a lot of pictures, a lot of what these things look like. So Amber, you just asked which section we're on. So we're in the middle of 8.1. 8.1 is all about the graphs of sine and cosine, and then 8.2 is about the graphs of the rest. So we're in the middle of 8.1. We're going to finish that and hopefully finish 8.2 as well. But before we go there, any questions on the homework? Anything from the homework sections we want to look at? All right, again, I'm going to take silence as we're all good. So with that said, then I guess let's go ahead and just refresh our memories about the graphs of sine and cosine. So what I'm going to do is I'm going to share my screen, and I'm going to go to Desmos again, my favorite graphing program, just so that we can take a look at these guys and remind ourselves how they work. So, you should be able to see my screen.
I don't care.
All right, so let me just set this thing so we can see it a little bit better, because right now it's a little bit wonky for us to see what's going on. So for the graphs of sine and cosine, I'm going to set my windows to be minus 2 pi to 2 pi for my x's. So that'll get me a good couple of cycles for this thing. If you want to ever play along and come to Desmos, to get pi, you just type pi, and it'll go ahead and give it to you. So then on the y-axis, I'm just going to go from minus 5 to 5, because I think that should be sufficient for us here. All right, so this right here, even though you can already see what's highlighted, you see that this is sine. But the way that we know that this is a graph of sine and not cosine is that it goes through the origin, right? The graph of sine goes through the origin and then starts this sine wave pattern, okay? So it's just a wave. And again, we get alternating maxima and minima. The maximum value is at 1. So we saw that. We always get 1 as the biggest y value out of this, the biggest sine value, depending on the angle. The smallest is -1. And so it just oscillates between plus and minus 1. It does have a whole bunch of intercepts, and those intercepts happen at every pi. So this right here is 1 pi. If we move over, that's 2 pi. If we go the other direction, minus 1 pi, minus 2 pi, and so on. So we see this pattern for sine, and it does repeat itself. And so we call this a periodic function. And the period is how long it takes to repeat. And in the case of sine, it's 2 pi. So if you start at 0 and you go out to 2 pi, what you're going to see is the exact same thing starting over. So here's the next from 2 pi. Now there's 3 pi, and so on. And so if I just kept shifting over, we just keep seeing the same picture over and over and over, repeating every 2 pi. Okay, so that was the graph of sine. So let me kind of bring it back here where we're near origin. So let me turn on the graph of cosine, but hopefully you all remember that the graph of cosine looks identical to this. It's just shifted pi over 2. And in the case of cosine, at the y-axis, it's going to have a maximum. Okay, so this guy now is in green. Let me turn, now we'll leave them both on. So here's cosine. But you notice cosine has its maximum when we're at an angle of 0. but it still follows that same process. It goes from a maximum of 1 to a minimum of -1. and it just keeps oscillating. It's got the same period. The intercepts are shifted as well. So instead of at the whole pi, these are at the half pi. So this is pi over 2. The next one is 3 pi over 2, and so on. So notice that the zeros for cosine are always at the max or the min for sine. And similarly with sine, its zeros are either at the min or the max of cosine. And that just comes from that pi over 2. All right, so hopefully everybody remembers that. Kind of important, these basic shapes, because now we're going to use transformations to change them. So any questions on this before I stop my sharing and we go to the whiteboard? All right, hearing and seeing none, I'm going to go ahead and stop share, and let's go to the whiteboard. So some things I want to remind you about. So first, let's talk about the transformations that we did on sine and cosine and what they did. So for example, I think we went generically, y equals a times the cosine of bx. And I'm just going to look at cosine, but sine, it's the same. It's just shifted over. So a, what this does is a vertical stretch. It's a vertical stretch or compress. If a is greater than 1, it stretches it. If it's between 0 and 1, it compresses it, right? So it shrinks it down. And what a is in the language of sine waves, we call this the amplitude. And so the amplitude is just a measure of how far it goes up and down. And I like to think of this as it's 1/2 of the vertical extremes. So if you just think about how far on a graph of sine or cosine, how far we go from the bottom to the top, amplitude is 1/2 of that. So it's from the midline to the top or from the midline to the bottom, but that's our amplitude. So that's what A does, is it just changes how tall the graph of sine or cosine is. And then what we saw with B is a a horizontal stretch compress. And so what that does is pushes it in or pulls it out, and that affects the period. Now, B itself is not the period, but what we find out is that the period is actually equal to 2 pi divided by B. The B just changes, it's the multiple, the factor of how stretchy this is horizontally. So our period is going to be off by that factor as well, but it's inversely proportional. We divide by B just because it's a horizontal thing, and horizontal transformations do the opposite of what you think. Okay, so if B is bigger than 1, we need it to compress. And so that's why dividing by B will shrink it down. And then if we have B less than 1, it should expand it. And again, dividing by B makes that happen. Okay, so we saw this last time, that we call these guys the amplitude and the period, and A and B, they affect amplitude and period, but they are stretching and compressing either vertically or horizontally, depending upon where it is. Okay, but the other things we can do, other transformations we can do, we can also shift up and down and left and right. So little quiz for class. Do you guys remember what we have to do to transform things so that we have shifts?
H and K.
Okay, so H and K are the letters that we use. Thanks, Adam. And then I see that Amber put in the chat, add, subtract. And we add, subtract. Sometimes it's H and K, it can be whatever letters, but it's the adding and subtracting that causes things to shift either up and down or left and right. So what we're going to do to this is we're going to include the potential shifts. And so our form now, instead of just being a cosine of bx, I'm going to put here bx plus c inside the cosine, and then plus D on the outside. And so this now allows for shifts. The plus D, this one is vertical. So this is going to make us go up and down. So depending upon what that D is, that will tell us how far to go. And its sign will tell us whether we go up or down. So if it's a plus, if it's a positive number, we're going to shift upward. And if it's negative, then we'll shift downward. Okay, so that's what D does. D is going to be the vertical shift. And then C, this is going to lead to a horizontal shift. So that's going to move us left or right. But this one is opposite of what you think. If it's negative, we're going to shift to the right. And if it's positive, we're going to shift to the left. So hopefully you remember that from transformations. We're going to play around with it today, so it'll kind of come back for you. But that's going to lead to a horizontal shift. But here's where things are a little bit different also with the horizontal. I don't know if you remember this, but when we have both a horizontal stretch compress and a horizontal shift, this number, whatever C is, isn't the horizontal shift. The horizontal shift is determined by it, but it's also determined by B. Now, in the context of trig, when we're talking about sines and cosines, we call that horizontal shift a phase shift. Because when we talk about these things, like we'll talk about them being out of phase, they're just translated a little bit differently. What it really comes from is if these things are time dependent. So if we're graphing something in terms of time, where our variable is t, if they're out of phase, they're out of sync in terms of time. So we call it a phase shift. But the phase shift is your horizontal shift. It's actually going to equal C over B. So we have to account for the fact that there was also a horizontal stretch to figure out how far we go. Okay, so is C the midline? Kiva just asked. No, C is not the midline. C is a horizontal deal. The midline would be D, because the vertical shift, you can think it took wherever that midline was at 0 and brought it up to D. So C is not the midline. It's it accounts for a horizontal change, not a vertical change. But this will tell us exactly how far we have to shift it. Which direction we shift will be dependent upon the value of C, whether it's plus or minus. All right. So, okay for that idea? I'm going to go ahead and mute everybody, just in case we're getting some weird feedback. But if you want to mute yourself, feel free, right? If you've got a question to ask, go ahead and click unmute or hit your space bar and go ahead and ask that question, okay? All right, so what we're going to do is we're going to kind of combine all of these and look at what this does to the graph. So let me give you an example of one with an A, B, C, and D. We're going to put them all together and we'll talk about what that should look like. And then we'll go to Desmos and we'll graph it and we'll see if we actually get what we think we should. So let's go with this. Let's go with 3 cosine of 2x minus pi minus 1. So notice I just gave you a whole bunch of things. We have an A, a B, a C, and a D, which means we're going to have all of these transformations happening. So here's what I suggest you do. First, just go with let's figure out what the different letters are. So we've got A is 3, B is 2, C is negative pi, and D is -1. So you notice that I keep the signs on these guys that are negative. I do that because it helps me remember what's happening, where we're going, what's going on. Plus, if you look at how I wrote it out, I had it as plus C and plus D, which means if these are subtractions, I'm adding the negative. Okay, so there are the numbers. Now let's think about what this does in terms of the graph. So A gives me my amplitude. So I know that my amplitude is going to be 3. So that means from the midline, I'm going to go up 3 to a max, and I'm going to go down 3 to a min. So the total top to bottom is going to be a difference of 6 because the amplitude is half. Okay, so we stretched it vertically. That cosine now is taller by a factor of 3. Okay, so let's think about what B does. So B, this affects our period. So our period is going to be 2 pi over B, which in this case is 2 pi over 2, or pi. So this tells me that my graph now is going to repeat in half the time. So we're going to see it repeat more frequently because instead of having to wait a full 2 pi, we're only going a single pi. So we've just compressed it horizontally, which multiplying by a number bigger than 1 on the inside tells me that. So that matches. All right, so there's my period. Let's think about what C does. C affects my phase shift. So let's get our phase shift. So we need to do C over B. So C is minus pi, B is 2. So our phase shift is negative pi over 2. So we're going to shift pi over 2. We're going to take all those points and shift pi over 2. But then the question is which way? So do we go right or left with this phase shift? All right, I'm getting a bunch of people throwing out right, and that's correct. We are definitely going to move to the right because of the fact that it's negative. So think about cosine would normally have a peak at the origin, or sorry, at the y-axis. It's not going to have a peak there anymore. Now its peak is going to be at pi over 2 to the right. So over at pi over 2. We'll draw a graph of it. I'll show you how this all goes together. Okay, so then lastly, we've got the D. And remember what D does. This is a vertical shift. So what this tells me is that the midline is now going to be at y equals -1. So instead of it being at the x-axis like we had before, I'm going to shift it down 1. So our center line is going to be at -1, and it's from there that I'm going to go up 3 and down 3 for my amplitude. All right, so before we try to draw a graph of this, any questions about how I went through this and found the different information? Okay, so I'm going to show you how we can graph this by hand. And then what we'll do is we'll go to Desmos and confirm that our graph looks good. All right, so let's try graphing this thing. So first thing I'm going to do, well, first thing I'm going to do is put on my axes here. But the first thing I do when I go to graph one of these things is I go to where my new midline is. So my new midline is at y equals -1. So that means that somewhere down here, which is -1, this is my new center line. So I just put a little dashed line here. Pretend that it's a line. Goodness gracious. Okay, so there's my midline. So the next thing I do is I mark out how far I'm going to go to get my amplitude of 3. So I need to go up 3, and I need to go down 3. So I'm just going to mark those so I know where my maxes and mins are going to be. So my maxes are going to show up here at 2. So they'll repeat, right? We know they repeat over and over, but they're going to be at y equals 2. And the minimums are going to be down at y equals minus 4. And again, they're going to repeat, but I know they're going to be down there. All right, so cool. So now that I've got that, the next thing I do is I take care of my phase shift. So let me go put some horizontal markings here. And these are going to be pi over 4s. Okay, so those were 1s. These are going to be pi over 4s. So that means like the second one is pi over 2. The fourth one is pi, then 3 pi over 2, 2 pi. Okay, so every other one is pi over 2. All right, so let's take care of that max. So that maximum, instead of being right here on the axis, it's been shifted over pi over 2 to the right. So I'm going to take that point, come over here to pi over 2, and I'm going to draw that maximum. So the coordinates of that point are pi over 2, comma 2. So when you do this, when you take care of your phase shift, always shift the point that's on the y-axis. Start with that point, because that's the only one that will move exactly how you want it to move. If you affect the period, then other things can occur. So I always start with that point, which is pretty easy because if it's cosine, it's just that maximum. If it's sine, it's just the 0, and we move it over. All right, so there's the phase shift, or at least for the first point. So now let's take care of the period, because that's the only thing we haven't done yet. Right? We haven't done anything with the period yet. So now let's take care of the period. So I know that the period is pi. So if I were to go 1 pi over, I'm going to get the exact same value, the same y value as where we are at a given point. So let's take this point that I know, pi over 2. The pi over 2, if I go over a pi, either way, I'm going to get a maximum. Well, since these are pi over 4s, I'm going to go over 4, which brings me to 3 pi over 2. So there's going to be another max that's at 3 pi over 2, 2. I could also go pi the other direction. Brings me over here. Oops, not too far. And so this would be minus pi over 2, 2. Because again, I just took a pi away. And then I could take another pi away, and it gives me another max, and so on. And I could keep going. So those maxima are going to occur every pi. All right, so what we actually have right now is a graph of all of the maxima. So that's pretty cool. But of course, we need to do a little bit more if we want to get a graph, a complete graph. We also need to know where are the minima. So the minima are going to be halfway between the maxes. Because when we looked at the graph of sine and cosine, those were from the minima. I want to back up real quick because Adana, you asked a question, and I'm sorry I didn't catch this earlier. You said, is the number 2 from B? And I want to know which number 2 are you talking about? Because there are a couple of number 2s. Were you talking about the number 2 that was where the maximum are?
I'm talking about the number 2, p over 2, the first point.
The-
P
oh, this
over
one
2
right
and
here?
yeah, and then you said y is equal to 2. That was my question. Like, how did you get the number 2?
Okay, so this point right here, the pi over 2, that came from our phase shift. And the phase shift is found by taking the c over the b.
Yeah, that one I got already, but then the
Okay,
number 2.
so, all right, so then this 2, that actually comes from taking our midline, this -1, and adding the amplitude. So we get our maximum values by adding the amplitude to wherever our midline was. So if you take -1 plus 3, that's where this 2 came from.
I got you. Thank you. I missed that already. Thank you.
You're welcome. All right, so let's go back and let's find the minima. And the minima are going to be located halfway in between the maximum. So if we look at, say, these two maximums, they're at minus pi over 2 and at pi over 2. Halfway in between that is going to be 0. So at 0, we're going to get a minimum, which is going to be down here at -4. So this is the point 0, -4, and I apologize. That's kind of getting caught into the equation. So the 0 comes from the fact that it's halfway between these two. And the -4, just like the 2, it's being found by taking that midline value and subtracting the a. So if we do -1 minus 3, that brings us down to -4. And then they're going to repeat every pi. So there's going to be another one here that's at pi -4. And the next one's going to be at 2 pi -4. And then there's going to be one over here that's at -pi -4, and so on. So there are all the minima. So we got our maxima and our minima. And now, of course, we know we just need to connect this with the sine wave, but I'm going to do one better. I know what shows up exactly halfway between a max and a min. If you go back and you look at the regular graphs of sine and cosine, we saw that halfway between a max and a min is a 0. Well, that 0 was the midline. So the way to think about this now is that between the maxes and the mins, if we're halfway, we're going to be exactly at the midline. So that means there's going to be a point right here on our midline, and then another one right here on our midline, another one right there on our midline, and so on. And so you're just, hopefully you notice that all I'm doing is I'm going half the distance. The way I've got it set up, each one of my tick marks is one of these special places. So, but I'm going from maximum to midline to minimum to midline to max, mid, min, mid, max, mid, min. It's just that same pattern over and over and over and over. So now we can just go ahead and connect those dots. And there is a graph of at least this portion of y equals 3 cosine of 2x minus pi minus 1. So that's the general process. If you ever want to draw one of these things, is just strip out all this information and figure out what they all tell you. Now, it's possible you don't have all of them. And if you don't have one of those pieces, it doesn't affect the graph that way. Like if there's no number out front cosine, the amplitude doesn't change. The amplitude is still just 1, and so it'll go up 1 and down 1 from the midline. Or if there's no D, there's no vertical shift. Or if there's no B, the period is still 2 pi. Or if there's no C, there is no phase shift. So if any one of them is gone, it's actually a good thing, because that's one less thing you have to worry about. But you can see that if you've got all of them, just take them one by one, and you'll be able to figure out what the graph needs to look like. So let's go to Desmos. All right, so Amber, you just said, how did I get the points on the midline? I went exactly halfway between the maxes and the mins. So think about this max was at pi over 2. The next min was at pi. So I go halfway between pi over 2 and pi. which is 3 pi over 4. And I get my midline. So just go half that horizontal distance. Smack dab in the middle between a max and a min is where we're on the midline. Does that make sense? Okay, good. All right, so let's go see how this compares to what Desmos says. So I'm going to share my screen again. And what you should see now is a graph of cosine. Just regular cosine is this kind of greenish one. And then we've got the graph of 3 cosine of 2x minus pi minus 1. So first things, notice that the maximum values are up here at 2. And in fact, if I hover over this point, you can see its coordinates minus pi over 2, 2. This one is pi over 2, 2. This guy's 3 pi over 2, 2. So those were all the points that we saw there. And then the minima are down here at minus 4. So there's our 0 minus 4. This is pi minus 4, and so on. Now, in terms of the midline, we don't really see the midline here. But if I were to graph, let me real quick graph y equals minus 1. So there's our midline. And now you can actually see where those points are. So here's that point, pi over 4, negative 1. That pi over 4 is halfway between the maxes and mins of 0 and pi over 2. And then we've got 3 pi over 4, and 5 pi over 4, and 7 pi over 4, and so on. So it's exactly what we got. Obviously a little bit faster because we're using the technology, but we're able to build it by just breaking it down piece by piece. And you can also see all the transformations that occurred. Let me get rid of this midline. But think about this graph of cosine. It's now been stretched. It's a lot taller. Well, that was its amplitude. It repeats faster, right? Like this one, the green one, here was a max. The next max was all the way over here on the other edge. In fact, in this window, you can only see, well, you can't even quite see, but you can see one max, a second max, and not quite a third, right? But the red one, you definitely see more than that, right? In terms of the maxes, there are 4 of them across the top. The mins, you can see there's 4 and almost a fifth. So we're getting more of them, which means the period has decreased. And then the transformations, you can see the horizontal shift because the maximum, instead of being at 0, is now over at pi over 2. So we shifted it over. And you can also see the vertical shift where the center line has been dropped. So anyway, this is the process. This is how we do it given a sine or cosine. And I showed you an example of cosine. Sine does nothing different other than it starts at the origin. So when we shift, we have to shift the origin appropriately. All right, so how do you guys feel about that? Not too bad? Okay, so in the real world, when we're actually out there in the real world, we use sine and cosine a lot because sine and cosine are great for any kind of information that repeats, right? It's got to be periodic, and also bounces back and forth between a maximum and a minimum. And there are lots of things out there in the real world that does this, that have these properties. So obviously a real thing would be waves. If we're going to talk about waves on the lake or on the ocean, clearly we're going to use sine and cosine for that. So things like tidal waves, and I don't mean tsunamis, I mean tidal waves, like the tides as they come in and out, they are waves. We can use sine and cosine to represent those and all that. So, or if we're going to talk about light waves or sound waves or anything like that. So clearly anything that's a wave, we're going to be able to use sine and cosine for. But it turns out that we use this for a lot of other things that are not waves, because of the fact that they have those two properties, that they repeat on a constant cycle and have a max and a min. And so a really good example of this is in weather when we talk about temperatures. specifically like average monthly temperatures. So take Lake Tahoe, for example. We know that it gets colder in the summer, in the winter, warmer in the summer, right? We know that it repeats because every year we're going to talk about average temperatures. January is going to be cold every year. July is going to be warm every year, right? And so it repeats. There is going to be a maximum. There is going to be a hottest time of year. There's going to be a coldest time of year. And so this is something that we can actually fit a sine wave to relatively easily. So let me show you. Let me share my screen again because I got this information earlier today and I wanted to put it in here. So I went and found the temperatures, the average temperature for South Lake Tahoe. Hold on 1 second here. I didn't share the right screen. All right. So here are the average temperatures for South Lake Tahoe. And you'll notice that here for the high temperatures, you notice our coldest month on average is January, which surprises nobody, I'm sure. And then you notice that it starts warming up. We get into the summer. Now June, we've got an average of 68.7, July 77.9, August 772, right? So it warms up in the summer and then it cools back down. And then of course, once we get to December, we start over. So it's definitely periodic. It's got a period of 12 months and there is a highest in July and a lowest in January. This next set is for the low temperatures. Well, let's not worry about low temperatures. We're just going to look at the high temperatures. Okay, so if you graph that, and that did not do what I wanted it to do. Okay, give me 1 second here. I'm gonna have to stop share and then reshare again. Okay, so you can see my Desmos screen now. And what I did was I actually put this data in. If you look up here on this first list, there are a whole bunch of points. And you can just take my word for it that as you go all the way across, you've got all the different points. But those are the months of the year. And in fact, I did 2 years worth. Let me see if I can arrow over just to show you so that there's month 7, 8, 9, 10, 11, 12. And then I started over with January again as month 13, February is 14, and so on. Okay, so I went ahead and did 2 years worth of average temperatures. Let me change the windows on this so we can actually see it because these values are significantly different. So let's on the y-axis, let's go from say 0 to 100. Or no, on the x-axis, sorry, let's go 0 to 25. That'll give us our 2 months worth. And then the y's, let's go 0 to 100. I just said 2 months, I meant 2 years. But we'll make our temperatures go from 0 to 100. And so there's our data. So what do you think? Does that look kind of like a sine wave? I mean, kind of, right? It's not perfect, but it definitely looks like it's oscillating. It's bouncing between a maximum and a minimum. It's also repeating, right? This was just 2 years worth of, I could put in another year, we'd see a similar thing. So it definitely feels like we could use a sinusoidal wave to graph it. So here's my question. What is the equation of a sine wave that fits that data? So let's see if we can find that. All right, so let me just remind you of a couple of important numbers that we're gonna want. I'm gonna write them on the board so when we get to the board, we see it. But a couple of things that are important. One is what the maximum value was, so the maximum average temperature. And the maximum was 77.9. That happened in July. Okay, so I'm going to write that on the board just so we have it. And then we also saw that the minimum was 38.6, and that happened in January. And other than that, the data isn't going to help us fit this graph. We're going to have to use our brains to figure out the values for A, B, C, and D to make this work. So I'm going to stop share so we can go to the whiteboard and see if we can figure this out. Okay, so I put up on the board here the max and min values, just so we've got them. And let's think about what we need to figure out. To get the graph of this thing, we need to figure out 4 things. Amplitude, right? So how far does this go from the midline up and down? Period, so that'll get us our B value. A phase shift, which will give us our C value. And then the midline, how far did the midline go up? All right, so to attack this, we're actually going to figure out amplitude and midline first. So let's just think about this. We've got a max at 77.9 and a min at 38.6. How are we going to figure out the midline? What could we do with these 2 numbers to figure out the midline for this graph? Any thoughts? So Diego says add and divide. What do you want to divide by? By 2? Okay, and so Amber just said find the average. Yeah, that's exactly it. We want to figure out halfway in between these 2. That's just the average. So the midline, this D, it's just going to be the max plus the min divided by 2. Always. It doesn't matter what those temperatures were. Like we could be looking at average monthly temperature in, Warsaw, Poland, and it would be the same idea. We'd get different numbers, but we'd still figure out that midline by doing the same. Okay, so let's go ahead and do this then. So we're going to get 77.9 plus 38.6. We're going to divide it by 2. So adding those things together, what do we get there? 116.5, I think. No, that's too much. No, that's right. Yeah, so 116.5, which then when we divide by 2, that gives us a value of 19.65, or 58.25, sorry. So this is 58.25. So that's the number that's exactly halfway in between those 2. And so that's how far we're going to have to shift up. So our midline is no longer going to be at 0. It's going to be at 58.25. All right, so you should feel good because we're halfway, or we're 1/4 of the way done. We got one of the 4 numbers that we need. Okay, now amplitude is the next thing we're going to get. So the question is, how do we figure out the amplitude? Ideas? No idea? Anybody still there?
Yes.
Thanks, Adam. I appreciate that. Okay, so how about this? We know amplitude is how far we have to go from the midline up or the midline down, right? We also know that it's half the total distance from min to max. So William just put in the chat, difference between top and bottom. if we get the difference between top and bottom, that's actually double the amplitude. So we can do one of two things. To get A, you can do max minus min divided by 2. So that's one way that will work. Okay, so you take half of that difference and divide by 2. Or you can take the max minus the midline. That will work as well. And that's what a couple of you guys have put up there. Like Diego just put difference between top and mid, and Kai also put subtract max from the midline. So if we look at the difference between the maximum and the midline, that would give us our amplitude as well. So these are two different ways you can do it. I suggest just doing max minus min divided by 2, because that way you're not relying on this D value just in case you made a mistake. So this would be then 77.9 minus 38.6 divided by 2. Or alternatively, take your 77.9 and subtract 58.25. So either way is fine. Either one will get you what you need. But if you do that calculation, you end up getting 19.65. So that's the amplitude we need on the graph. All right, so let's just look at what we get if we have only those two. No, let's not. Let's find the period as well. Let's use the period to find B. So remember how we find B. B is related to period, and in fact that the period is equal to 2 pi over B. So B, if I rewrite this, is going to be 2 pi divided by the period. So if you know the period, if you know how long it takes to repeat, you can figure out B. So how about this? For this specific example, how long does it take for this pattern to repeat? Specifically, think about like a max. We've got our maximum temperature. How long until we get our next maximum temperature? Okay, so Kai just put in there 1 year. Yeah, good. This is going to have a period of 1 year. We're assuming that the average temperatures are the same, which, okay, in reality is not a good assumption because of the thing, you know, like global climate change and all that. But let's just go with that it repeats, and so it's the same every year. So our period is every year, but I'm going to do this in months. Since all my time values are months, since I had averages for January, February, March, and so on, let's do this in months. So we know that in this case, our period is 12 months, which means our B is going to be 2 pi over 12, which reduces down to pi over 6. So it's actually that easy always to figure out B. You just take 2 pi and you divide by your period. All right, so we're close. The only thing we don't have yet is a phase shift. So let me do this. Let me draw what we've got so far. We've got y equals 19.65 cosine of pi over 6 x t plus 19.65. And I apologize for running out of room here. But this has everything in it except the phase shift. So what I want to do is I want to actually graph this versus our data, because I think it will help us figure out how we figure out our phase shift. So let's go back to Desmos and let's draw a picture of this thing. Okay, so there's our data. Let me, I'll turn this guy off for a second. I can make that easily enough later. So let's go 19.65 cosine of pi divided by 6 times x plus, oops, it's not 19.65, it's 58.25. All right, so on the screen, you can now see the data, so our purple dots, and the graph of this thing without a phase shift. Let's pull it over here a little bit. So at this point, you should feel pretty good about our three values, because if you look at how far we go up and down, right, however far we go up and down, it definitely matches the data. And if you look at where the center line seems to be, it seems to be just about right. And in terms of the distance from peak to peak on the blue graph versus the purple data, appears to be about the same as well. All right, so Amber's question of how do I know if it's cosine or sine? It's either one I want. I pick. So I picked cosine for a very specific reason that I'll explain in a second. But you can use cosine or sine. The only difference is you're going to have a different phase shift, right? Cosine and sine are already related by just being off a little bit. And so that will just change your phase shift. So, plus I like cosine better. I definitely am biased when it comes to these functions. Cosine is my preferred. But anyway, so, and Kai, you were right. It doesn't really matter. And sometimes one is easier than the other. All right, so the last thing we have to figure out then is phase shift. So here's why I use cosine. We know cosine has its maximum when we're at 0. It's really easy to figure out how far that maximum has to move, because all I want is for that maximum to move over to the maximum month. And on our list, that was pretty easy to see. We saw that that maximum happened in July. And so the number for that month is 7. So I need to move this from 0 to 7. All right, so how far is that? That's like the stupidest, most easy question to answer, right? To go from 0 to 7, I need to shift by 7. Now, if you're at a 0, or if you're using sine, you'd have to figure out, okay, how far do I go from the midline to the month that's got my middle temperature? That's hard to tell, but it's really easy to tell which month has a maximum temperature. So if I'm ever doing something where I've got maximum and minimum values given, I immediately go to cosine because I think it'll be a little bit easier. All right, well, let's go to the board and let's see if we can figure out what this should look like, and then we'll come back and see how well our graph matches. All right, so the last thing is we need a phase shift of 7. And we also need that phase shift to be 7 to the right. Because for cosine, again, because I chose to do cosine, it's got a maximum at 0. That maximum has to end up being at 7, which is to the right 7. So since it's right, that means it's negative. So we have a phase shift of -7. And what I know is that that's equal to C over B. So phase shift is always C over B. So C then is going to be -7 times B. And we just calculated B a minute ago. We found that that was equal to pi over 6. So we end up with that C then needs to be a -7 pi over 6. So if I put that all together now, this is what my function is going to look like. I've got y equals 19.65. So we already saw that amplitude was good. I'm going to go with cosine of pi over 6 times x minus 7 pi over 6. And then I'm going to add to that the vertical shift, which I've forgotten now what that number was. It was 58.25. So the only difference between this and the one that we just graphed is it's going to be shifted over 7. So now the question is, how well does that fit our data? So before I go and draw the graph of this on Desmos, any questions on how I got that? All right, seeing none and hearing none, let's go take a peek. Okay, so you should see my Desmos window. And let's take this thing and let's put in -7 pi over 6. So we'll put in that horizontal phase shift. So it's going to disappear for a second. And so here is the graph, including the phase shift. So I want you to notice that this definitely fits the data better than what we had before. Is it a good fit? Yeah, that's a little bit subjective. I would argue that it's, decent. If you look at some of these points, right, like you look at this string, well, the maximum and the minimum are dead on, which was by design. When we shifted over 7, it got us so that our max and our min were at those places. And then you look at these other ones, they're pretty close. So between July and January, so in the fall and early winter, this fits pretty well. Not so much for the spring and late winter, so we're off quite a bit. Turns out that our temperatures are not really, they are sinusoidal-ish, but there's a little bit of a lag in the late winter spring. We tend to stay colder than it would look like if it was truly sinusoidal. But at least the max and the min are exactly where we want it. So it's a fairly decent fit, and it didn't require us to do anything really crazy. In fact, we're able to do all of this without technology. If you wanted to do a best fit sine wave, like there are ways of doing that using statistics and calculus, that would make this fit a little bit better, but it's way more work. So if we want just a simple, this is about what it is, you can see how well this fits. Notice that it probably would be a little bit better fit if we slid it over a little bit more. You notice that these 2 points, the maximum in July and then the one in August, they're not that separate from each other. They're not that different. So it might even argue that, well, we really should shift over like 7.5 months. Well, let me show you what happens if we do that. If I make this 7.5 months instead of 7 months, now we are lagging a little bit in the spring, but now we also have that in the fall. Is that a better fit? I don't know. We could adjust this even again. But according to the data, it's something around this. So temperatures are a place where we see this, where we get this max and min business. But another place that we see this would be, let's say, hours of daylight. If you wanted to model the number of hours of daylight at a specific location, that's sinusoidal. We get the most sunlight in the summer and the least in the winter. A lot of places, precipitation, the amount of rain you get, is sinusoidal. So there are lots of things out there that have absolutely nothing to do with triangles, because remember, trigonometry is all about measuring triangles. We haven't talked about triangles at all today, and yet everything is trig, right? So one of the reasons I love trig is it's far-reaching and it goes everywhere. All right, so how are we feeling about the graphs of sine and cosine? You going to be able to produce them yourself? Maybe with practice. All right.
Got it.
Oh, sorry, go ahead, Adam. What was that?
Just saying I got it.
Okay, cool. Thank you. Also just got a thumbs up from Amber. Thank you for letting me know that there are people out there. All right. So the one other thing that can happen with sines and cosines, and specifically their graphs, is we can flip them over, right? You can use a negative out front to flip it over. So sometimes it's even better than using sine or cosine. Sometimes you want to use negative sine or negative cosine. That just sort of depends. Their graphs look exactly the same, just with different transformations, different shifts. So you actually can do any sine curve an infinite number of ways. There are the four main ways with sine, cosine, negative sine, and negative cosine. But you can also phase shift all you want, periods and all that. So when it comes to finding an equation for a bunch of data or a curve that looks sinusoidal, remember that you're finding an equation. You're finding one of the many. And so every one of you guys, like if I gave an exam that had like a picture of a sine wave and said, give me the equation of this, every one of you could give me a different equation and still be correct. Okay, so I just mentioned that because sometimes when you're using online resources and you look up an answer or something, it may not match what you did, and that doesn't mean that you're wrong. It just means it's in a different form. So be careful about that. I often get that question, students will be like, I don't know what I did wrong here because this doesn't match the back of the book or whatever. And it's not that you did something wrong, you just did something different, right? And so in math, different isn't always bad. Anyway, okay, so there's the graph of sine and cosine. So now the question is, what do the graphs of the other things look like? What about tangent, cotangent, secant, and cosecant? So let's go take a look at those, and we'll talk about their domains and ranges and periods and all that good stuff, kind of like we did with sine and cosine. Obviously, it's going to be different because they're constructed in a different way, but let's see what we've got. Okay, so I'm going to go back to Desmos, and we're going to draw a graph of tangent, doing the same thing we did with sine and cosine, which was plot the points. So we'll take the data that we know, and we will plot their points. So let me just, while it's coming up here, I'm going to shift things back to where we need to be. So hopefully now you can see my window. I'm going to go back and change this so that we're going from minus 2 pi to 2 pi, and our x. And then for our y's, I think what we'll do, let's go say minus 5 to 5 right now. Okay, so we're from minus 2 pi to 2 pi on the horizontal, vertical from minus 5 to plus 5. So you'll notice I've got a whole bunch of stuff plotted here. Let me start just with this set of data. This data, the one that starts 0, 0, pi over 6, 1 over root 3, pi over 4, 1, and so on. Those are the values for tangent. If you go back to our chart and what we built for our special angles, these are the coordinates for tangent. So the angles in radians followed by their tangent values. Now, I didn't plot all of them. I just put in the values that are in the first two quadrants. So this is from 0 to pi over 2, and then from pi over 2 to pi. Remember that at pi over 2, we have an undefined. So at pi over 2, we don't actually get a value of tangent, but we do get these values. And you can start kind of connecting the dots here and see that we're going to get some sort of curve that appears to be growing bigger. As we approach pi over 2, it's going to be undefined at pi over 2, but we can get as close as we want to pi over 2, and that's fine. It turns out the tangent just gets larger and larger and larger. So what we end up getting here is a vertical asymptote. So let me go ahead and graph tangent over this data. And you can see how it fits it perfectly, as it should. And so you'll also notice that there is a vertical asymptote here at pi over 2. On one side, we go towards it. We get a number that keeps growing bigger and bigger and bigger. So we say that this goes to positive infinity. On the other side, it keeps getting smaller and smaller. So it starts approaching negative infinity. All right, now I didn't graph the other points, but if we were to continue from pi and start working our way over, these are going to be the third quadrant angles. We're going to get some positive numbers. And if we were to plot the points, we'd see the same positive numbers. So you get dot, dot, dot. If we go to the fourth quadrant, again, plug in the points we know, we'd get dot, dot, dot. And so you can see this repetition. So this looks significantly different than sine, right? This is no longer a wave at all. But this is what the graph of tangent looks like. So let's bring up some facts about this. And I'm going to put these on the board so that when I get there, we'll have all this information. But let's just start with things that we recognize. So first of all, I want you to notice that its domain is not all real numbers. There are problem spots, right? There's this vertical asymptote at pi over 2. There's another one at 3 pi over 2, and so on. And so we've already seen that. When we built that chart, we had places where we wrote undefined or does not exist. So in terms of the domain, it turns out that the domain for tangent is everything except those pi over 2, 3 pi over 2, those odd half pi's. Okay, so I'm going to go ahead and write that on the board, that the domain is all x's except those that are the half pi's. So let me change it so that the little window in the corner is actually the whiteboard. So hopefully now in the corner you can see the little whiteboard. So I wrote up here for tangent that the domain is all x not equal n pi over 2, where n is odd. So we have a problem at the odd half pi's. And I know that that window is really, really tiny, so you might not be able to read that. Like if you're on a phone or something. I'll come to this board and make it bigger in a minute. All right, but we have domain issues. But other than that, other than those odd half pi's, we're good. Now let's think about the range. So range is how far we go up and down. So how far can we go up and down on the graph of tangent? So if we just start with how far down do we go? Well, if we follow one of these branches or whatever you want to call it, they're going to continue to go down, 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 down forever. And so we can actually go as far as negative infinity. And then in terms of up, well, you can follow the same kind of idea. And those are going to go forever upward till we get to positive infinity. So the range for tangent is all real numbers. And this is significantly different than sine and cosine. Because remember, sine and cosine were restricted. We were trapped between plus and minus 1. But for tangent, we get whatever we want. All right, so there's that. Notice the intercepts. The y-intercept is at 0, 0. And then the x-intercepts, they happen every pi. So we get one at pi, 2 pi, 3 pi, 4 pi, and so on. So on the board here, I'm going to write the y-intercept is 0, 0. And then the x-intercept intercepts, I should say, are at 0 or n pi, comma 0. So every whole pi, we're going to get another intercept. And then the last thing I want to talk about with this graph before we look at the others is the period. And you'll notice here that the period, it's not 2 pi anymore. It doesn't take a full 2 pi to repeat. In this case, I know that we were using maxes before for sine and cosine. We don't have those for tangent. Use the intercepts. Notice that the intercepts, since they repeat every pi, you can actually just take a strip of this that's length pi and see the repetition. Or think about it this way. Look at one of these little branches. Right? These guys get repeated. So we have the same shape show up again and again and again and again. And that is between minus pi over 2 and pi over 2, which is 1 pi length. So tangent's period's a little bit shorter. It repeats every pi. And I think we actually saw that when we talked about the chart, but you can definitely see it on the graph. Okay, so there's information we see about tangent. So let me go back to the window, or to the whiteboard here, so you guys can see that information a little bit bigger. But again, the domain, it's all x except for the odd half pi's. The range is all real numbers. We pass through the origin, that's our y-intercept, and then our x-intercepts were at the whole pi's, and our period was pi. All right, so that's tangent. Now, you can probably guess that cotangent's going to be similar. We saw sine and cosine were similar. Well, tangent and cotangent are going to have similar graphs, but they're not quite as similar as sine and cosine. Sine and cosine, all we did was we shifted over. This one, there's a bit more to it. There's not just a shift. There is a shift, but there's a little bit more to it as well. So let me go back to that window on Desmos so we can draw a picture of it. All right, so let me go and draw a cotangent. I'm just going to change this guy from a cosine to a tangent. Okay, I'm going to change the color as well. All right, so the greenish one was tangent, and now this purplish one is cotangent. So what did you see here other than just a phase shift? What else happened? Can you describe it? All right, so Amber just said it flipped, right? So notice that now instead of increasing, because tangent increased, right? On this green line, we keep going up as we go to the right. Now with cotangent, we're decreasing. So cotangent, while there is that shift, the zeros now are at the half pi's, right? So there's our minus pi over 2, pi over 2, 3 pi over 2. Those are now our intercepts, where before those were asymptotes. There's a shift, but there's also this flip. Okay, so they just go the opposite order. But if you know the graph of tangent, you can get the graph of cotangent pretty easily. So in terms of cotangent, things that change, if we look at the domain now is different values that we can't have. And it's in fact the whole pi's that we can no longer have. but its range is still the same. So just like with tangent, cotangent's range is all real numbers. It does go forever up and down. In terms of the y-intercept, this is a little bit weird. This one doesn't have one. There is no y-intercept with cotangent. If you look at this axis, there's nowhere that that purple line crosses the x-axis. I'm going to turn off tangent just to help you see a little bit better. Now 0 is an asymptote, but if you go back and you look at our chart when we built this thing out, cotangent, we weren't able to have anything anyway. We wrote DNE or UND or whatever. It wasn't defined there. So there is no y-intercept. But in terms of the x-intercepts, well, they're now at the half pies. So I'm going to write the same thing that we did for the domain of tangent, but this is going to be n pi over 2, comma 0, where n is odd. And then lastly, the period. Notice that the period is still pi. If you know the graph from 0 to pi, you can take that same strip and just copy and paste. So it definitely shares some features with tangent, but has a little bit of a difference because of the fact that it's a different function. And in terms of its graph, we see it shifted over and flipped over. There's a reflection as well. So let's go back to the picture or the whiteboard here. And so I've got it written out. But again, notice the R is the same, the range is the same, the period is the same. But in terms of like the domain of one is actually where the x-intercepts of the other are. So that's kind of a nice little feature to recognize, because that can help you remember if you need to know that information. All right, so there are the graphs of tangent and cotangent. Now, these can be stretched and compressed and shifted the same way. But when it comes to those things, we don't have amplitude anymore. Amplitude doesn't make sense for tangent. So if there's a number out front, it's just a vertical stretch or compress. We don't actually have a name for it. And it does, it just changes all those tangent values by that multiple. We can change the period. If there's a b, now the period, instead of being 2 pi over b, is going to be pi over b. So let me just write that real quick. If we go to something like y equals a tangent of bx plus c plus d. All right, so they're going to do the same things. The d is going to be a vertical shift. It still brings up the, I guess, quote unquote midline, even though midline doesn't really make sense if we're going from minus infinity to infinity, but I think you know what that would mean in a graph of tangent. It's that place where we're changing from going up kind of curved down to going up curved up. But the big difference here now is that the period is going to be pi over b, not 2 pi, just pi. But that's because of the fact that its period was pi to start with. So that's really the only difference if we throw in transformations with tangent and cotangent. All right, so there are those. So let's hit secant and cosecant. Let's look at their graphs just so that we can be complete here. And you're going to see that they also are similar to each other, but they're quite different than the graphs of tangent and cotangent, and also sine and cosine. So I'm going to go back to share my screen, and we'll go back to Desmos again. All right, so I have one more set of data that you can probably see up here. This one that starts 0, 1, pi over 6, and so on. So this was secant. This is the numbers you get for secant, at least the first few. So here's 0, 1, pi over 6 gave us 2 root 3 over 3. Pi over 4 gave us root 2. Pi over 3 gave us 2. And then these were the negative values. So there are some of the points. And I could go ahead and graph all the points. And if I do that, what I get is something that looks like this. So here is a graph of secant. Whoa, that's way different, right? We had a sine wave before that just kind of oscillated up and down, and then tangent had those weird things that went to plus and minus infinity. And now secant, this is an alternating set of smiles and frowns. That is not a math technical term, that is a Bruce term. But these are alternating smiles and frowns. So we see a smile, it goes to a frown, then there's a smile, there's going to be another frown, and so on, right? If we just keep moving over. So it's alternating series of smiles and frowns. Okay, real quick, do not call these parabolas. Please do not call them parabolas. I know that they kind of have a similar shape, but they're not. Okay, so you're used to seeing one of these things be a parabola, but this is not a parabola. That's why I just call them smiles and frowns. That way we don't have to worry about that they're technically parabolas or not. Okay, but now let's talk about domain and range and all that good stuff. All right, so first of all, domain. There were domain problems for secant. If you go back and you look at our chart, everything that we built, there were problems for secant because they were the problems where cosine was equal to 0. And if you look at this, it's at the same places as tangent. Let me actually turn tangent on for a second. And you can see how tangent and secant both start going up kind of with the same vertical asymptote. And the same thing where it comes down, it catches the frowns. So secant and tangent actually look a lot alike as you get closer and closer to those asymptotes. But let me write up on the board here. Now we're going to look at secant. In terms of its domain, it's the same as tangent. It's the x's that are not equal to the half pi's where the n is odd, right? So the odd half pi. So that's actually kind of nice that we don't have to learn a new domain. It's the same as tangent, but there is a restriction. So then if you look at the range, this one's a little bit different too. In terms of how far can we go down, well, we are going to be able to go down to minus infinity. You get on one of those frowns, as you approach the asymptotes, you're going to drop down. And as we come up, we keep getting y values. Y values are great, but then there's a place where the y values quit. And there's a bunch of y where we don't actually get any values. And so if you look at this frown, the top point on the frown is -1. So that means in terms of its range, we're going to get everything from minus infinity to -1, including -1. And then for a while, we don't get anything until we reach this y value, where we're now at the bottom of the smile, which you notice happens at 1. And then when we're on a smile, we're going to be able to go all the way up to positive infinity. So that gives us a range of 1 to infinity. So we actually stick those together to get the range for secant. All right, so in terms of the y-intercept, again, we see the y-intercept is 0, 1. And for x-intercepts, this doesn't have any. There's nowhere where we actually cross the x-axis. So then the last thing we want to include on here is a period. And it's pretty easy to see that for this one, the period is going to be 2 pi. In order to get a complete graph, if we were to cut and paste, we would need both a smile and a frown. And that's going to have to go over an interval of length 2 pi. But we already saw that, I think, that secant had a period of 2 pi. So there's a graph of secant. And while I'm here, let me graph cosecant. So I've already got it set up. So the black one was secant, the red one is cosecant. And if you look at these are exactly shifted over, just like we saw with sine and cosine. In fact, it is the same shift, pi over 2. If you want to go from secant to cosecant, you just have to shift over pi over 2. So it's also a set of alternating smiles and frowns. So in terms of the properties that we saw, many of them are the same. But for cosecant, some things that have changed now are the domain. Now the domain problems are not the odd half pies, it's the whole pies, because we shifted over by pi over 2. The range is still the same. The frowns give us minus infinity to minus 1, and the smiles give us 1 to infinity. The y-intercept, now there isn't one, because of the fact that there's an asymptote at 0. There still are no x-intercepts, and the period is still 2 pi. So just like the graphs of sine and cosine are related, and tangent and cotangent are related, secant and cosecant are related, they look like this. So one more thing before I go to the board. Again, if you didn't catch all this, I'll make the board bigger so you can see it in a second. But I want to show you one more thing, which is I want you to see how the graphs of secant and cosine relate, and cosecant and sine relate. Because we already know that they're reciprocals of each other, right? Like secant is the reciprocal of cosine, and cosecant is a reciprocal of sine. So since I've got these two together, I'll do cosecant and sine. So this is the graph of cosecant, and let me turn on the graph of sine. And this should have been one of those ooh, ah moments, right? Amazing. Look at how these graphs are related. These smiles and frowns that show up on the graph of cosecant, they end up touching the graph of sine at the maxes and the mins. And those vertical asymptotes are occurring wherever sine was equal to 0. Well, I just want to prove to you that the same thing happens if we have secant and cosine. So let me change this guy to a cosine real quick. Ooh. Oh. All right, same story, right? The alternating smiles and frowns show up at the maxes and the mins. Well, the reason I wanted to show you this is how you can get the graph of secant or cosecant really quickly. If you graph, like this one, we want secant, start by drawing cosine. So create your cosine wave. We know that it's got its max when we're at the y-axis, and then we go, right? Well then, at every max, draw a smile. So there was the smile at the max at the axis. Here's the next smile that occurs at the next maximum. And then draw frowns at all the mins, and there you go. It's a real quick graph of secant. So cosecant, do the same thing, just start with sine. Okay, so let me go back to the board so y'all can write down this stuff if you didn't catch it. But you can also then kind of figure out by the graphs of secant and cosecant, there aren't a lot of things that actually follow those patterns as well. And so they're not nearly as useful in the real world. If you want just truth from Bruce, reality is sine and cosine are the important trig functions. The rest of them, I mean, they have use, but not nearly as frequently. Tangent has some uses in weird situations, but for the most part, especially if we're not dealing with triangles, it's sine and cosine. So you really want to know those graphs well. All right, so hopefully that was enough time for you to grab that stuff off the board. What we talked about with secant and cosecant. Okay, so you've now seen all 6 trig functions and what their graphs look like. You can transform them just like any other kind of function. The sine and cosine, those transformations are more important, and they all have names, like phase shift and amplitude and stuff like that. But really the goal is being able to take these functions and apply them to situations where we have periodic functions that are bouncing back and forth between some maximum and minimum value. Okay, so I'm actually at a point where I think I want to stop. I know that we're a little bit earlier than normal, but there are a couple of things I want to share. First of all, I need to give you a word of the day. It's been a while since we've had a word of the day because we had an exam and stuff, and I actually remembered it today. So I think today, in the usual theme of random stuff that's on my desk, I think today is going to be pretzel, which is also very appropriate. I don't know if you know, but yesterday was National Pretzel Day. Yeah, there's a national day for anything. So we'll make the word of the day be pretzel, okay? And then I see Bella just threw something on the chat window here. Let me see what this says. Do you think it's possible that the fabric of reality acts like a 3D graph of all 6 trig functions interacting? No, probably not. I would say, and I know you wrote he, so you may not actually be looking for a real answer, but you just opened a can of worms. So, because I teach modern physics as well pretty regularly, and one of the things we do talk about is what space-time looks like, and what space-time actually looks like, nobody knows. We have a bunch of theories and all that, but I would argue that really the graphs of these other things are only there because of their relationships to sine and cosine. Yes, it is a huge can of worms. So I'm not going to go too deep into this, but these things in 3 dimensions as well, like you can take the trig functions and go to 3 dimensions, but really the sine and cosine, you can get ripples like that in 3D. You can kind of get alternating, think of it as like little mountaintops, and then little valley chunks that repeat regularly. We do see that in certain molecular construction, like if you look at when atoms are put together and stuff like that, you can get sort of a repeating 3D sine and cosine business. But I've not run into anything that involves secant, cosecant, and thank you for amusing you, Bella. Yeah, it's not hard for me to start talking about stuff like this. So then Amber said, so these waves are like music, electromagnetic waves, and colors. Yeah, you can actually describe all of those using sines and cosines. Sound waves. Sound waves are what we call pressure waves. They actually progress because the molecules in the air are getting pushed together, and they get kind of a vibration going on, which like if you were here in person, as I speak, my vocal cords are vibrating the air. That air vibrates until it gets to your eardrum, which then vibrates your eardrum, and then your brain interprets it. Obviously, through technology, there are things that alter, that are taking my pressure wave, reading it, sending it as an electromagnetic signal, which then gets turned back into a pressure wave. Anyway, but yeah, that pressure wave we could describe with sine and cosine, and in fact we do. And then light is another good example. This one's not a pressure wave. It's done in a different way. You don't actually need a medium for it to go through. That's why you can actually have light go through space, but sound doesn't. But yep, so you use it there. So electromagnetic waves are, the light we see are electromagnetic waves, but that also includes things like gamma rays and X-rays and ultraviolet light and all that. But yep, we use sine and cosine for those as well. To a physicist, to someone who does like physical science, sine and cosine are always present. They're always there. They never go away. And I could continue to give you a huge list of things where we use sine and cosine. So, including just the structure of matter. If you want to talk about things like where electrons are relative to the nucleus of an atom, if you put up what we call potential barriers, which are energy barriers that they have to overcome, they can sometimes pass through and they look sinusoidal. So we actually have what we call wave functions for matter. Like this is one of those trippy things that everything that makes you up acts both as a particle and as a wave. It's called the duality of matter. And so even if you just want to get to what makes you up, what, that uses trig as well. So anyway, for those of you who are going to go down the science path, get really familiar with sine and cosine, really familiar, because the better you know them, the more sense other things are going to come or are going to make when you get there. And it'd be better for you to be comfortable with the trig functions, and so you don't have to concentrate on that. You can concentrate instead on the weirdness, like, things being both waves and not waves at the same time, which is, yeah, mind blowing. Anyway, so that just reminded me before I forget, because you guys got me off. Thanks for doing that, Bella, by the way. And also, you guys notice that if you ever want to not talk trig for a while, just get me started talking science. But the other thing I wanted to mention is we are going to have a quiz next time, and the quiz is going to be on section 8.1. I will send out a message through Canvas just to remind you guys. So that's going to be the graphs of sine and cosine, a little bit of what we did today in terms of like phase shifts and amplitude and all that. But we'll do kind of the same thing that we did last time where we had a quiz. So on Wednesday, I will stop us probably right around 12:30, turn on the quiz. In fact, I will have the quiz set to turn on. No, I'll turn it on as soon as we're done talking, because I don't want people to, in case I'm running a little bit longer, to go switch to the quiz. But I'll turn it on as soon as we're done with lecture, and then you guys will have like I did last time, I think a half an hour to get it done and uploaded. So we'll do same kind of thing that we did 2 weeks ago with the quiz, but plan on that for 8.1. All right. So other than that, I don't think I have anything. So this week, yes, Yair, as in 2 days, this Wednesday. So pretty much just plan on every Wednesday we don't have an exam, that there will be a quiz. Okay, so like I said, I'll put that information up on Canvas as well, just so that you've got it. Anyway, so any other questions before we call it a day? All right, well, with that, have an awesome week. I'm going to go ahead and stop the recording here.